So let's talk about BitTorrent. It's a fascinating internet application with a lot of interesting algorithms and approaches. There are reasons why it works so well. BitTorrent allows people to share and exchange large files. A BitTorrent client requests documents from other clients. So that a single client can request from many others in parallel, BitTorrent breaks up files into chunks of data called pieces. When a client downloads a piece from another client, then it tells other clients it has that piece so they can download it too. These collections of collaborating clients are called swarms. So we could talk about a client joining or leaving the swarm. A client joins a swarm by downloading a torrent file that tells it information about the file, such as how big it is, the size of its pieces, and how to start contacting other clients. It used to be that a torrent would name a tracker, a computer that keeps track of what clients are part of the swarm. When a client joins the swarm, it requests a list of other clients from the tracker, then starts contacting these clients over TCP. A BitTorrent client can have on the order of 100 open TCP connections at once. After trackers started receiving a lot of unwanted attention in the late 2000s, most clients transitioned to using tracker-list torrents. These torrents contact a host that tells them how to join something called the Distributed Hash Table, or DHT. A DHT is a way to map a hash value to a node where a set of nodes supporting that DHT can change a lot, yet you can still find the node. So rather than use a centralized table for this lookup, the mapping is actually distributed across all of the participating nodes. It's basically a way for some nodes to collaboratively store some data. In this case, they're storing lists of which clients are part of a swarm. BitTorrent breaks a file up into n pieces. Each piece is 256 kilobytes or larger. This size is intended to ensure a TCP stream transferring the file is long-lived enough that its congestion window can grow to a reasonable size and so support good throughput. But BitTorrent also breaks up pieces into sub-pieces so that it can request parts of pieces from multiple peers and so reduce latency. A piece is also the unit that BitTorrent uses to check integrity with. A torrent contains the SHA-1 hashes of each piece. SHA-1 is something called a cryptographic hash function. It's the primitive used in message authentication codes. A strong cryptographic hash function has the properties that, given a hash, it's really hard to create a piece of data that has that hash value. That means that if the torrent says that the hash of piece 5 is h, it's hard to come up with a piece that isn't piece 5, which also has hash h. So you can't start replacing the pieces of the torrent and screw it up without a client noticing that the hash isn't right and retrying. So this actually brings up an interesting story. In 2006, HBO had a new series called Rome. There were several different torrents for it, each of which had very large swarms. But many people found their clients couldn't download the series. Looking into it, it turns out there are a bunch of very fast peers that many clients were connecting to and downloading from. But these peers provided pieces that didn't have the right hash. So a client would download the piece, find the hash was wrong, throw away the piece, and retry. Back then, the clients assumed that this was just an error and so kept on requesting from the same peer. So many clients would just enter an unending loop of trying to download the same bad piece. The hypothesis was that this was an effort by HBO to prevent downloads. Nowadays, clients can blacklist peers that serve up many bad pieces. BitTorrent clients, when connected, periodically exchange information on what pieces they have. A client tries to download the rarest piece among its peers first. If a single piece becomes unavailable, nobody can download the file. Also, if only a few clients have a piece, they'll become a bottleneck for downloading. This is called the rarest first policy. The one exception to the rarest first policy is when a client reaches the end of the torrent and only needs a few more pieces. At this point, it requests for pieces from multiple peers. It does this to counter the edge case of asking for the last piece from a very slow peer and having to wait. So this final step means that the client might download multiple copies of subpieces and waste swarm bandwidth. But since there are often 1,000 or so pieces in a swarm, this cost is small and so worth it. So BitTorrent clients exchange metadata with each other to learn what pieces they have. A client starts requesting pieces from its peers. But if you send data to every peer, you'd have lots of very slow pieces. Instead of having 100 slow TCP flows, BitTorrent tries to have a smaller number of fast flows. The idea is you send data to peers who send you data. That way, peers who contribute can download faster. This creates an incentive to send pieces to peers. The way this works is through choking. Most peers are choked, and so you send no data to them. BitTorrent measures the rate at which it is downloading from each of its peers and picks the p best of them. P is usually a small number, like 4 or the square root of the number of peers. It then chokes these p peers and sends data to them. This algorithm is called tit for tat. You send data to nodes that send you data. One problem with this algorithm is that it doesn't explore much. There could be a really good peer out there who could send you data very fast if only you started sending some data first. So every 30 seconds or so, BitTorrent unchokes a random peer. This peer might then find its way into the p best. The BitTorrent tit-for-tat algorithm seems pretty robust. You send data preferentially to other peers who send you data. But it's not perfect. There was a nice paper in 2007 that proposed something called BitTorrent, which selfishly tried to game the system. And it did. Using BitTorrent, you could increase your BitTorrent throughput by 70%. The basic observation in BitTorrent is that in standard BitTorrent, a peer tries to share its uplink capacity evenly across its unchoked peers. So if a client has p unchoked peers, then each one receives 1 over p of its uplink capacity. But once you're in this top p, you get all of this. So the trick is that you want to give a peer just enough to make your way into its top p and no more. You should then spend the extra capacity trying to get into another peer's top p. So this way you give everyone just enough that they unchoke you and maximize how many peers unchoke you. It's a nice result. They also found that if everyone used BitTorrent, performance can improve slightly, but you get the most benefit if you're the only tyrant. The URL here links to the paper. So that's a basic overview of BitTorrent. Your client downloads a torrent file, for example, over HTTP. This describes the file to download and how to find peers to download it from. BitTorrent breaks the file into pieces, and peers exchange these pieces. They connect over TCP/IP and exchange metadata so they know what the distribution of pieces is over their part of the swarm. A client then tries to download the rarest piece first in order to balance availability. Clients upload data only to their top p downloaders, so most of the peers are choked and receive no data, and the client gives data to those who give you data using a tit-for-tat algorithm. To discover potentially good new peers, the client also randomly unchokes a peer periodically.